Today in module 5 we are going to see about interrupts and interrupt programming. So what is an interrupt? So an interrupt is an external or an internal event that interrupts the microcontroller to inform the microcontroller that a device needs the service. Whenever a device needs the service, in that case the device is going to interrupt the microcontroller so that it can obtain the service from the microcontroller. Okay, so there are two ways to do that. One is called as the interrupt method and another one is called as the polling method. In the polling method, the CPU or the microcontroller continuously checks whether any device need to be served. Okay, so in the polling method, the microcontroller keeps on checking whether any device needs the service. So if the device needs the service, then it going to serve the device. That is, it checks the condition. If the condition is going to match, then it is going to service the device. Okay, so after that the microcontroller goes for serving the next device. So like this, it serves all the devices in the round robin fashion. That is called as the polling method. In polling method, the microcontroller continuously keeps checking or polling the device that needs to be serviced. Okay, so that is the polling method. So coming to next is the interrupt method. So in the interrupt method, what happens is the microcontroller will not check the status or the condition whether the device is needs the service. The microcontroller, or sorry, the device, whenever it needs a service, then the device sends an interrupt signal to the microcontroller to say that it needs a service. Okay, in that case the microcontroller halts or discontinues whatever it is doing. Okay, and then it goes and services the device. So after that, once the device servicing to the device is over, in that case, after that it continues with whatever it was doing earlier. Okay, so this event you can think as, in the home you are sitting and you are reading a book. Okay, so and suddenly somebody comes and knocks the door. Okay, so knocking the door, I can consider it as an interrupt. Reading, so microcontroller, nothing but you are doing some task of reading. So whenever the doorbell knocks, in that case what you will do is you keep a bookmark, so to have that, so later when I come back I should start from there. Okay, you keep a bookmark, and then you go, so you go and open the door, nothing but you service the device, service whatever the service required, you are going to do that. Later, once the service is over, you are going to come back and start with where you have left. The bookmark which you have kept is nothing but it indicates where you are left, and you are going to start from there. The interrupt routine can be related to this concept. Okay, so for each interrupt, for each device interrupt, there is a routine has been written at a specific memory location, and it is called as the interrupt service routine or the interrupt handler. Okay, so this is what. So whenever any device needs a service, the device notifies the microcontroller by sending an interrupt signal. Upon receiving the interrupt signal, the microcontroller halts whatever it is doing and serves the device. The program which is associated with the interrupt is called as the interrupt service routine or the interrupt handler. For each interrupt, the program is written at a specific location. For each interrupt, the program is written at a specific location, and we call it as interrupt vector table. That we'll see later. Okay, so in the 8051 microcontroller, so totally we are having five, so usually they say six. Okay, so one two are nothing but the hardware interrupt, that is int0 and int1, and two are nothing but the interrupt created by the timer overflow flag, that is tf0 and tf1, and another one is nothing but the interrupt from the serial communication, that is the transmit interrupt and the receive interrupt. For serial communication, both for transmit and receive, we are having only one interrupt, the ti and ri serves for one interrupt, and also the reset is taken to be one interrupt. So whenever the reset occurs or whenever the system starts, that is nothing but, so the reset interrupt is going to be executed. Okay, so that is about the six interrupts in the 8051. So for polling method, I already told where the microcontroller continuously keeps on checking whether the device needs the service. If the device needs the service, then it goes and service the device. So once it does service the device, then it goes for the next device and keeps on checking whether the device needs the service. Like this, it goes on checking all the devices in the round robin fashion. So that is the polling method. So what is the advantage of interrupt, or the what is the interrupt versus polling? Which one is better and which one is not disadvantageous? We'll see. Okay, in the polling method, as we discussed, microcontroller continuously keep the checking whether the device needs the service. So because of which the microcontroller will not be doing any task, it's just checking the status whether the device needs the service or not. So for example, we have seen in the timer programming where, so once I start the timer, I'll be monitoring the timer overflow flag, that is TF flag. So using the instruction JNB-TF. So is nothing but I'll be just checking when the timer overflows and when the TF flag is set. So this is nothing but it is a waste of time. The microcontroller is just doing nothing, just keeping the status of the flag. Okay, so microcontroller in any application, it is supposed to do lot many things. So it cannot waste its time just keep monitoring the status of some flags. So because of which the polling method will not use the microcontroller time or the microcontroller service efficiently. Okay, so we say that polling method is not so efficient because the microcontroller time is just wasted in monitoring the status of the device. Okay, so but interrupt method, it is efficient because the here in case of the interrupt method, the microcontroller will not keep on checking the status of the device. Whenever the device needs a service, it interrupts the microcontroller. So because of that, the interrupt method is more efficient compared to the polling method. So previously we have seen the timer programming using the polling method, where we are using the JNB instruction to check whether the timer flag has or the timer has overflown. Now here again we'll see the timer programming, where we'll be using the interrupt method. So whenever the timer overflows, it interrupts the microcontroller to say that I have overflown, so carry out whatever the action you need to do. So thus such things we'll see now, how to do the timer programming using the interrupt method. Okay, so that is one thing. Microcontroller time is efficiently used in interrupt method. Microcontroller time is not efficiently used in the polling method. Okay, so again in the interrupt method, so here in the polling method, all the devices are served in round robin fashion. Okay, there is but in real cases or in practical cases, so some devices, whenever they require the service, there will be some emergency happens. In that case, that device need to be serviced first. So such thing is not present in the polling method, but in case of the interrupt method, each device can be assigned the priority. Whenever the higher priority device it sends the request to service the device, then microcontroller first goes and service the higher priority device. So in case of the interrupt method, the priority can be assigned to the devices, but in case of the polling method, the priority cannot be assigned. So it serves the devices in the round robin fashion. Okay, that is one disadvantage. Next, again interrupt, in interrupt method, the microcontroller, okay, the microcontroller can enable or disable the interrupt. So if it is doing some service which cannot be interrupted, in that case it can disable the interrupt. So there is an option in case of the interrupt method, where is the one register called as the interrupt enable register. Using that, I can disable or enable the interrupt. And also for priority setting, there is one register called as the interrupt priority register, where we can assign the priority, that we are going to see next. So in polling method, it is not possible to enable or disable the interrupts. Okay, so that is about interrupts versus polling. So finally we conclude that the interrupt method is much more better than the polling method. In all the applications, the interrupt method only is used. Okay. Okay, as already have discussed, I've told you there are totally six interrupt in 8051, actually five, but reset is also called as one interrupt, and finally it's going to be 6 interrupt. Okay, the first one is reset interrupt, that is power on reset interrupt. Okay, the second is two hardware interrupts, so that is nothing but INT0 and INT1. Okay, so two hardware interrupts. The port 3 pin 2 and port 3 pin 3 are for the hardware interrupts. Already you know that the port 3 are multiplexed, it's having the multifunctional. Out of that, port 3 pin 2 and port 3 pin 3 are reserved for interrupt 0 and interrupt 1. Okay, so that is 3. So next, two interrupts for the timer, that is TF0 and TF1. Already you know that TF0 and TF1 are the two interrupt for the timers. Okay, so next, serial communication has a single interrupt that belongs to RI and TI, receive and transfer interrupt flags. So the RI and TI together, it constitute a single interrupt. Totally they are going to be 6. One is power on reset, two interrupts for the timers, and two interrupts, the external hardware interrupts, and one is nothing but the serial communication interrupt for RI and TI. So totally there are going to be 6 interrupts in the 8051. Okay, so already we have seen that whenever an interrupt occurs, so in that case the microcontroller halts whatever it is doing and it goes and services the interrupt. Okay, so for each interrupt there is an interrupt service routine or the interrupt handler written. Okay, whenever the corresponding interrupt is invoked, then the microcontroller goes and executes the interrupt service routine. That is, whenever the interrupt is invoked, the microcontroller is directed to go to a particular memory location where the interrupt service routine is there. Okay, so for each interrupt there is a location, or there is a number of memory location allocated for each interrupt. So once the interrupt is invoked, directly it goes to that memory location. So in some cases the interrupt service routine is written there only. In some cases they have directed again to some other address where the interrupt routine is written. Okay, so nothing but for each interrupt, so whenever it is invoked, the microcontroller automatically goes and fetches the data from the particular memory location. So for each interrupt there is a certain number of memory location allocated or assigned to each interrupt. So the group of memory locations set aside to write the interrupt service routines is called as the interrupt vector table. So the interrupt vector table is nothing but it is the group of the memory locations set aside for the interrupt service routine, that is called as the interrupt vector table. Okay, so we'll see about the interrupt vector table. Okay, so on the reset, whenever we power on reset or whenever we press the reset button, what happens? The PC is loaded with a 0, which means that the program execution begins from the memory location 0. So because of which, whenever we are writing the program, the first byte of the program has to be placed in the memory location 0 always. Okay, so but for the reset, so this is considered, reset is considered to be one interrupt. So for the reset, so whenever the reset happens, automatically it goes to the ROM location. In the table it is given that the ROM location address is 00, so it goes to the 00. Okay, so there, so previously you have seen that whenever the reset happens, okay, so assuming that if we are not using any other interrupts, what we have done is from the 0 only we have written the program. But in our application, if you are using the interrupt, in that case I cannot write the complete program starting from the 0th location. So in some program you use the concept that when in the 0th location, so we started with org0, then we said that ljmp, so ljmp to go to the some location. Okay, so ljmp to the 3000h, so then we started with org 3000h and we have written the program. So because for the reset, so from 0 1 2 only 3 memory locations are reserved. From 3, so you see from 3, so the memory location is reserved for the external hardware interrupt INT0. Only 3 locations are reserved for the reset. So if the program, my program is having the external hardware interrupt and all, in that case I cannot write the complete program starting from the 0h, because of which what we have done is, so initially three locations are left for the reset. There we have written either the SJMP to some address or LJMP to some address, and we are going to that location, and there we are supposed to write the program. Okay, so for reset, when the three memory location 0, 1, 2 is kept as the is kept. Okay, so whenever the reset happens, PC is loaded with a 0 and it comes there, it sees. Okay, so again here again we have shown the program code. Okay, so it sees, it comes there, so it sees that, oh, LJMP to some location it's given, so it goes to that location. Okay, and writes the complete program. So previously, so in smaller programs where we are not using the interrupt concept and all, so we can write from the 0 only. Okay, so that is the case. So next, for the reset, the raw memory location is 0. So for the external hardware interrupt, okay, so for the external hardware interrupt int 0, the location is from 3. So from 3 to till a for the int 0, from 3 to till a. So only from 3 to till a, that is nothing but 8 bytes. Okay, so 8 bytes are for the int 0. So in some cases with only 8 bytes I cannot write the complete program. Again, what we do is we can write the jump on address like LJMP to some location, and we can write the complete program there. So it applies to all the things. So all the interrupts, they are having just only the 8 bytes of the location. Within the 8 bytes, if I can fit the program, I can write the program there only. If I cannot fit the program, I can go to some other location like this, what we said, LJMP to some location. So then there we can write the program. So whenever the interrupt int 0 happens, it directly, the PC is loaded with the 03, it comes there, it checks in that location. If the program is there, it executes that. If you have written some LJMP or SJMP, it again goes to that location and executes the interrupt service routine. Okay, so that is for external hardware. The ROM location is from 03, so it starts from 03, ends to 0A. For timer 0, that is TF0, the interrupt service routine is located at the address 0B. So from 0B to 1 to, again only 8 bytes for the TF0. Okay, so what I said earlier, it applies to for all the interrupts. So only for all the interrupts when the 8 bytes of memory location is allocated. If your program is small enough to write in that locations, 8 locations, you can write there. Otherwise, you can put a SJMP or LJMP in those locations, and you can redirect the microcontroller to execute the interrupt service routine written at some other place, as we did in case of the power on reset. Okay, so this was already we have seen, as we did in power on reset. Similarly, we can do for all other interrupts. Okay, so the next is external hardware int1. It is located at the address of 0013. TF1, timer 1 overflow flag, that is from 001B, and serial communication RINTI, so from 0023. Whenever RINTI is going to be high, suddenly the PC, so whatever the microcontroller it is doing, it halts, and the PC is loaded with what address? From the 0023 address. So there it fetches the byte, whatever the program have written, that program byte has been fetched, and it will execute the program. Okay, so this is about interrupt vector table. The interrupt vector table, so indicates, or it indicates the ROM location which is vectored, or which is the microcontroller is vector to execute whenever the interrupt happens. Steps in executing an interrupt. Whenever the interrupt occurs, what are the steps the microcontroller carries to execute the interrupt? That we'll see now. Okay, so first thing is, it finishes the instruction it is executing, and it saves the address of the next instruction. The address of the next instruction is there in the program counter, so the content of the program counter is stored onto the stack. Okay, so the address of the next instruction is saved onto the stack. Okay, so that is the first thing it will do. Okay, so I already have given the analogy of interrupt to a general routine of you are reading a book. Okay, there you have kept up the bookmark. The bookmark is nothing but after you service the routine, you come back and start from reading where you have left. That bookmark is nothing but I can relate it to saving the content of or the content of the PC, that is the address of the next instruction onto the stack. That is the first thing. Second thing is nothing but it also saves the status of the interrupts. This is an optional one, but the contents of the or the status of the interrupts are not stored onto the stack. It will not save it onto the stack. Okay, so third one is, you already know that whenever an interrupt occurs, so then the PC is loaded with a particular address based on which interrupt. So already you have seen the vector interrupt vector table. Okay, so if reset happens, the PC is loaded with the 03. If int 0 happens, the PC is loaded with the sorry, reset happens, PC is loaded with the 0. int 0 happens, then PC is loaded with the 03. So and similarly timer 0 tf not interrupt happens, then the PC is loaded with the 0b. Okay, so it jumps to a fixed memory location as given in the interrupt vector table that holds the address of the interrupt service routine. There can be the address of the interrupt service routine, or the interrupt service routine itself can be returned in those memory location. It is an optional one. Okay, so if the address of the routine, so nothing but some LJMP or SJMP is written in that address, in that case the microcontroller goes to the interrupt service routine, jumps to the interrupt service routine and executes the interrupt service routine. Okay, so at the end of the interrupt service routine, there is an instruction called as RETI, that is nothing but the return from interrupt. Okay, so there is an instruction called as RETI, that is the return from interrupt. So that instruction, so that executes. So normal subroutine, you are having the RET instruction. Whenever it is an interrupt subroutine, then you are having the RETI instruction. So that RETI instruction, so what it does is similar to your return instruction. So it is nothing but it is going to pop the top 2 bytes from the stack into the PC. So what you have stored onto the stack, you have stored the address of the next instruction onto the stack. Once the subroutine is over, the last instruction is RETI, that is nothing but the return from interrupt, is nothing but the interrupt service routine is ended and you should go to the place where you have left earlier. So that is nothing but where you have kept the bookmark. So where you have kept the bookmark is nothing but you have stored the content of PC onto the stack. So you are going to pop the content of the stack or into a PC again. So okay, so the top 2 bytes of the stack is stored again back to the PC. So now the PC is loaded with the address where you have left and the program execution continues there. Okay, and also the RETI, it is having an extra job of clearing the interrupt flags for timers and external hardware interrupts, that we'll see in detail later. So whenever RETI is executed, then the top 2 bytes from the stack is popped onto the PC, and also it also clears the interrupt flags for timers and also the interrupt for the external hardware interrupts. Okay, so this is the steps that the interrupt carries to execute the interrupt. Okay, so that is nothing but it finishes whatever it is doing and it saves the address of the next instruction onto the stack, and the PC is loaded with, so the PC is loaded with the particular address based on which interrupt it is. If it is a interrupt 0, the PC is loaded with the 03 address, is nothing but PC jumps to a particular memory location in the interrupt vector table. So there it going to execute the interrupt. So nothing but again in those location you have return a jump address, it goes there and it executes the interrupt service routine. At the end of the interrupt service routine, you are having the RETI instruction. That instruction gets the control back to the main program. That is nothing but it is done by popping the content of the stack from content of the stack back to the PC. Okay, so that is done. So this is what the steps that need to be carried out whenever you are executing an interrupt.